what we learned so far? Let us do a little bit of review. We learned that we have a function in one variable, y equals to f of x. We can generalize the idea to a function in two free variables, like z equals to f of x and y. So we talked about the domain of these functions. The domain of a function in one variable is a subset of R, and the domain of a function in two variables is a subset of plane. So as you guessed, if I generalize the idea to a function in three free variables, the domain is going to be a subset of the space. We're going to talk about that later. We also talked about the graph of the function, which is the set of all points with three coordinates, x, y, and z, such that z is equal to f of x and y. Last time we used some online websites to actually help us easily visualize functions in two variables. Today we're going to start talking about level curves. What are level curves? Level curves are curves of graph of a function that actually help us to understand and visualize the graph better. So we are on page 3, the definition of level curve. Level curves. Since we're not just using one curve, we use a family of curves to actually visualize the graph. Level curves of a function. Especially we're interested in functions in two variables when we are talking about level curves. Later on, we see we have level surfaces if we have functions in three variables. So level curves of a function are curves that are from solving equation. So to find level curves, you need to set an equation. What is that equation? The equation is take the definition of your function and set it equals to a constant like k. K is a constant. K can be 0, k can be 1, 2, 3, k can be negative number. That depends on the definition of the function. So they actually use those to create maps. So what they do, they take functions in three variables with two free variables, like this case. Suppose you have this function here, the graph of the function in three-dimensional space, 3D. What they do, what are these k's? You are actually setting the z, or the height, equals to a constant like k, and you're actually slicing the graph of the function. Those slices and go like this. So the outcome of the slice of f of x and y equals to k actually gives you some portion, that portion of this graph, which is in this case is going to be something like this. Then you use another k, you slice one more time. F of x and y equals to another constant, a constant. You get another slice on your graph, which is. And you continue this process to actually visualize these curves. Remember that when you're talking about curves, you're talking about graphs in two-dimensional space. Curves, 2D. not 3D. So eventually in XY plane, we can actually see the graph, level curves of the graph are like this. Again, they usually use this method in map making. Very well, so we are on page 3, still on page 3, and we have an example. This example says, hey, you have a function and your goal is to find some level curves of that function. Let us start. So let me erase this portion. Example. Find level curves of function is given as f of x and y, which is equal to 6 minus 3x minus 2y. And in this special case, the k values, constant values, the height, all of those heights are given. It says suppose k is equal to minus 6, suppose k is equal to 0, suppose k is equal to 6, and it has 12 as well. So for these k values, we're going to find level curves or just curves in xy plane. Well, let us start. So to find level curves of this function, we need to set f of x and y equals to each k. How many k's do I have? 1, 2, 3, and 4 k's. So one by one, I'm trying to solve these equations. So let k be equals to minus 6. F of x and y is 6 minus 3x minus 2y equals to minus 6. Okay, here you can say that I have like 3x plus 2y equals to 12, and you have just a linear equation to graph. You can leave it as it is. You don't have to solve it because it's just a line and you can easily graph this line. Let us graph it. Okay, I think I need more space. I'm going to just erase this part of the board. This is our x-axis. This is our y-axis. Okay, if I plug in 0 here, my y is equal to 6. So suppose 6 is here. If I plug in 0 here, my x is equal to 4. So it's going to be here. The first line passes through these 2 points in 2-dimensional space. Please. So here you have 3x plus 2y equals to 12. This is for my first k. I'm going with that. Let us move on to the second k, which is equal to 0. So let k be 0. What's the meaning of that? It means that I have to set the function equal to that k, which is 0 in this case. I have 6 minus 3x minus 2y equal to 0. My k is 0. And start solving this line. You can just leave it as 3x plus 2y equals to 6. Your goal is to graph the second line. Let's graph it. So if x is equal to 0, your y is equal to 3. If y is equal to 0, your x is equal to 2. So it's going to be here. If you connect these 2 points, you get a parallel line to the first line. So in this case, you have 3x plus 2y equals to 6. This is the second level curve. Well, you might say, okay, my next k is equal to 6. I'm going to plug that in. 6 minus 3x minus 2y is equal to 6. So in this case, 3x plus 2y is equal to 0. So you have your line passing through the origin, and of course that line is going to be parallel to these lines. So this is your third line. 3x 2y equal to 0, and you can just continue this process and solve it for k equals to 12. So when k is equal to 12, let's see. We get 3x plus 2y. Let me write it down here for you. Let k be 12. So we get 6x, 6 minus 3x minus 2y equals to 12, or 3x plus 2y equals to minus 6. Again, if you plug in 0, your y is equal to -3, and then your x is equal to -2. As you can see, we don't even have to just find these points. We can just follow the pattern here and connect these. And then graph a parallel line. So you might say, hey, can I use other k values? Of course, you can continue this process from negative ones to positive ones. You get the rest of the level curves. So let us take a look at our website, visualize this function. Here we go, one of our websites that helps us to visualize the whole thing. It's math3d.org. So let us write down this function, which is 6 minus 3x minus 2y. So let me just minimize the range here. 5 and 5, -5 and 5. So as you can see, here you just have a plane and the intersection of some planes with fixed z values are going to be lines. Those are your contours or level curves in xy plane. Okay, guys, take a minute or two. Sketch the level curves, then we go over it together. In the meanwhile, if you have any question, please use chat. So first of all, a question for you. Can k be negative? So to find level curves, you need to set the function equals to each of those k values. Set g of x and y, the definition of g of x and y, which is your z, equals to k. K is equal to 0. Let k be 0. So your g is square root of 9 minus x squared minus y squared equals to 0. Raise both sides to the second power. You get 9 minus x squared minus y squared equal to 0, which is equation of a circle centered at the origin with radius 3. So here you have a circle with radius equals to 3, and the center is at the origin. Okay, let's graph this. X-axis, y-axis. Suppose 3 is here. Let me see. I'm going to the smaller ones. So 3 and 3. The first level here is a circle, just a curve. It's not a disk, just a curve. So this is x squared plus y squared equals to 9. So we're done with the k equal to 0. What about k equals to 1? Let k be 1. So you have square root of 9 minus x squared minus y squared equals to 1. Raise both sides to the second power. You get 9 minus x squared minus y squared equals to 1, or x squared minus y squared is equal to 9 minus 1, which is 8. So in this case, you have a circle with radius equals to square root of 8. 2 point something. So radius is square root of 8. Center is again at the origin. Okay, it was 3. 3 minus 3 minus 3. Now you have square root of 8, which is, okay, let's say 2.2, 2.3. Negative square root of 8 and negative square root of 8. They have ugly circles. That's it. So this is circle with equation x squared plus y squared equals to 8. Well, you might say, hey, what if I plug in 2? If you plug in 2, then you have 9 minus x squared minus y squared equals to 4. So you get a circle with radius square root of 5.
Professor, the sign of what?
So this is a plus, x squared plus y squared equals to 8. Thank you. Very well. So let k be equals to 2. In this case, we have square root of 9 minus x squared minus y squared equals to 2. Or in this case, we have x squared plus y squared equals to 9 minus 4, which is 5. Radius is square root of 5. And the center is again 0 and 0. Okay, perfect. Suppose square root of 5 is here. This is square root of 5, square root of 5, minus square root of 5, and then minus square root of 5. Let's connect them together to have our inner circle. And finally, if you plug in 3, let k be 3, then you have square root of 9 minus x squared minus y squared equals to 3. What's the meaning of that? it means that x squared plus y squared is equal to 0. The only point, only numbers that satisfy this equation are 0 and 0. 0 and 0. What's the meaning of that? It means that the origin is part of the level curves of this function. In our website, we can just type this 9 minus x squared minus y squared. Okay. So this is the graph of the function. And if we slice the graph of the function, we get circles. That makes sense. Just look at the behavior of this function. If you slice it vertically, the intersection between each plane and the graph are circles. So suppose z is equal to 1. Connected, okay. With 3. And then if z is equal to, for example, 2, very well. Do you see the intersection? The intersection between the plane and your graph is just a circle. So let us just increase the range here, 4 and 4, so you can have a better visualization of this circle, which is your level curve. Here we go. You can actually see the intersection between your plane and your function. The graph of the function is nothing but a circle. You can continue this process. You can add another object, explicit surface, z equals to 1. You can use a different color, hopefully. No, it doesn't let us do that. Okay, second checkpoint. So let's sketch the level curves of the following function. H of x and y equals to 4x squared plus y squared plus 1. Try to use the website, visualize this function, then do it algebraically. Okay, let us go over this. So in this question, k is not given, k is missing. And so how many k's should I assign to this? First, I'm going to figure out how to write the equation of the level curves. Then it's easier for me to have an equation. After that, I can assign different k's to my level curves to solve for my level curves. So let us set h of x and y equals to k. What is k? K is a constant. Well, what do I have here? I have 4x squared plus y squared plus 1 equals to k. At the same time, I know 1 and k are constant. So what I'm going to do, I'm going to subtract 1 from both sides. And what do I get? I get 4x squared plus y squared equals to k minus 1. Well, this is very familiar. When we learned about cross sections, we learned about a circle like x minus a squared plus y minus b squared equals to r squared. We also learned that if the radius is not fixed, we have an ellipse, a minus a squared over h plus y minus b squared over k equals to 1. So we define equation of a circle and also equation of an ellipse. So it's very familiar for us. Take a look at this. Now, if k is not equal to 1, I'm allowed to divide everything by k minus 1. So what do I get? I get 4x squared divided by k minus 1 plus y squared over k minus 1 equals to 1. Very well. We can rewrite this side as x squared divided by k minus 1 over 4 plus y squared divided by k minus 1 equals to 1. Compare these two equations. You have a family of ellipses. So, our level curves are family of ellipses. This is equation of an ellipse. You have x squared over h, y squared over k equals to 1. Okay, guys, let's take a look at our graph here. We have z equals to 4x squared plus y squared plus 1. Very well. This is your function. This is the graph of the function. As you can see, it's not a sphere. It is curved. And down here, you can actually see the level curves. Level curves are not circles. These level curves are all ellipses. So you have family of ellipses. You can actually add objects, explicit surfaces, like z equals to 2. Do you see that? The level curve, the intersection between the plane and your curve is not a circle. This is just an ellipse. Very well. On page 5 of the notes, we have definition of functions with more than 2 free variables. So mathematically, you can add as many free variables as you want. You can actually form functions in n-dimensional space. So there is no limit to that. So we can form functions in more than 2 free variables. So you can define a function like w equals to f of x, y, z. Here you have 3 free variables. What's the problem with that? The problem is it's very hard to visualize. Note that it is very difficult to visualize a function in 3 variables. Why is that? Because you have to visualize the graph in 4-dimensional space. So the graph of this function is equal to the set of points x, y, z, and w, 4 coordinates, such that x, y, z, and w are real numbers. So I expect you to ask, how do we analyze these types of functions? So instead of working with level curves, we're going to introduce level surfaces to analyze these functions. We use level surfaces. How do we find level surfaces? You take the definition of the function and you set it equal to a constant. To find level surfaces, we set f of x, y, z equals to a constant like k. Our last example on page 5. Example. Example says, find the level surfaces of the following function. F of x, y, and z. As you can see, you have a function in 3 free variables, and it is equal to x squared plus y squared plus z squared. Guys, again, this function is a function that you can visualize it in 4-dimensional space, which is very hard. Not impossible, but we need computers with very high speed. Okay. To find level surfaces, guys, we are working with level surfaces, not level curves. If you say, hey, I have level curves, it means that you are working in 2-dimensional space, not 3-dimensional space. To find level surfaces, we set the function, which is x squared plus y squared plus z squared equals to k. K is constant. Well, we can stop here. You can say that, hey, I know what this equation is. This is equation of spheres. But we know that this is equation of spheres. If k is equal to 0, Then you have x squared plus y squared plus z squared equal to 0, which is actually the origin in three-dimensional space. 0, 0, 0. If k is equal to 1, then you have a sphere centered at the origin with radius equals to 1. This is a sphere with radius 1 and the center 0, 0, and 0. If k is equal to 2, you get a sphere with radius square root of 2 and center at the origin. This is a sphere with a radius equals to square root of 2 and center at the origin. So to graph this function, you get x squared plus y squared plus z squared. Hopefully we can graph this. Equals to 1. So as you can see, you have spheres here. So you can assign any value to k and actually change it to 2, change it to 3, change it to 4, and you get spheres that share the same center. So we get concentric spheres, level surfaces. It's not just one surface, it's a family of surfaces. So let us start 14.2. We're going to talk about limit, our favorite topic from Math 1A. There you go, 14.2. Limit, then we're going to talk about continuity. So let us do a little bit of review. How do you take the limit of a function? Limit in one variable. So if you have nice functions, like a polynomial, like sine, cosine, polynomials, three functions on their domains. If you have exponential functions, and so on, nice functions, then the limit of the function is equal to the value of the function by plug in the value. Then the limit of function, then x approaches a is f of a. So let us use f of x here. We have the same thing in functions in two or more variables. So, for example, suppose you have this function. Let function f of x and y is given as x squared y cubed minus x cubed y squared plus 3x plus 2y. So what do you have? You have a polynomial function in x and y. Instead of having just one variable, you have two variables. That's absolutely fine. Find the limit of f of x and y, x and y. So you need to assign numbers to both coordinates, x and y. While x and y approaches 1 and 2. 1 and 2. So it's the same as like saying that, hey, find the limit of function x squared minus x cubed plus 3x. While x goes to, for example, 1. You have a polynomial, and then you plug in the value to find the limit of the function. Okay. So here, my x is 1, my y is 2. I just directly substitute these into the function. I have 1 squared, 2 cubed minus 1 cubed, 2 squared plus 3 times 1 plus 2 times 2. Direct substitution. So here we get 8 minus 4 plus 3 plus 4, which is 11. As x and y in xy plane, in xy plane 1 and 2. As x and y approaches the points 1 and 2, your z value is getting closer to 11. X and y approach 1 and 2. Our z value approaches 11. That's the limit of the function. So these are nice functions. We don't have any problem with them. Direct substitution helps us to find the limit. Okay, let the actual fun begin by giving you this function. Okay, let me change my marker. So we are on page 2. So suppose I give you this function. I give you x squared minus y squared divided by x squared plus y squared, and I'm going to send x and y to the origin. X comma y goes to the origin. What is the limit of the function? Remember in Math 1a, in functions in one variable, if you have a function like f of x equals to x squared divided by, let's see, I'm going to have something on the denominator that makes the whole thing equal to 0. I'm not going to use this as something on the denominator that makes the function 0 over 0. Let's have this one, x squared over like x x squared minus 4. If I plug in 2, minus 2. Yeah, this is not that bad. While x goes to limit of f of x, while x goes to 2. So you say that, hey, if I plug in 2 here, I get 4 minus 4 divided by 2 minus 2, which is 0 over 0. I can either simplify this or I can use L'Hopital 0. So to find this limit, we can either simplify the function or use L'Hopital 0. But how about this function? Here you have two variables, x and y. So your goal is to try to get rid of one of these variables. So eventually you can apply that rule if that's possible. So our goal is to reduce the number of variables. So what we're going to do here, we're going to use lines or functions that has variable x in them, like y equals to mx, equation of a random line. Or we can use y equals to square root of mx, y equals to mx squared, y equals to mx cubed, and so on. So this is the general technique that we are using. Note that either of these functions, they passes through the origin. This point is the origin. The function that I'm defining are the function that are passes through the origin. What's next? After simplifying your function, if you have an expression in M, then you say that the limit doesn't exist. So let me write it here. So to find the limit of function f of x and y, use y equals mx or y equals to mx squared or y equals to mx cubed or y equals to square root of mx or any other function that passes through the origin. That passes through the origin. After simplifying your function, after we simplify the function, if you have an expression depending on M, then the limit doesn't exist. Does not exist. This is your first method. So why am I using using these general functions instead of getting rid of some of these variables. You can do that, but there is no guarantee to get to the actual result. So, to find the limit, or to check to see if the limit exists, to check to see if the limit exists, let us use y equals to mx. It means that wherever I see y, I substitute that with mx. So I have the limit of x squared minus, now I have mx squared divided by x squared plus parentheses mx squared. And note that this new function doesn't have any y in it. So now you're just sending x to 0. We simplified this function in two variables into a function in just one variable. This is equal to the limit of x squared minus m squared x squared divided by x squared plus m squared x squared, x goes to 0. It is super easy to solve, of course. Here you can factor out x squared, 1 minus m squared, divided by x squared, 1 plus m squared. And while x goes to 0, you can cancel out x squared and x squared. The outcome is equal to 1, this limit is equal to 1 minus m squared over 1 plus m squared. So that depends on m. It means that I can select a value for m, you can select a value for m, other people can select different values for m. So you get different limits. You don't get a unique limit. So since this expression depends on m, and we can assign many values to m, the limit does not exist. Okay. So you might say that I don't want to use a general function like y equals mx. I want to plug in different values. Okay, let's see. We can also plug in different values for our variables when x and y approaches to am. So in this case, since x and y approaches 0, we might say that, hey, I want to set x equal to 0, then I want to set y equal to 0. So I want to just eliminate x and reduce the variable into y. I get limit of 0 minus y squared over 0 plus y squared, which is, so y goes to 0, which is negative y squared over y squared, which is negative 1. You might say, hey, I want to plug in y equal to 0 into the function. I get the limit of x squared minus 0 divided by x squared plus 0 while x goes to 0, which is equal to 1. As you can see, you get different values. So the limit doesn't exist. Since 1 is not equal to -1, the limit doesn't exist. I don't recommend this method. You have functions that they don't respond to this method. Try to absolutely feel comfortable plugging general functions. Let us take a look at the graph of the function. This is the graph of your function. X squared minus y squared divided by x squared plus y squared. So as you can see, at the origin, look at the behavior of the graph of the function. The limit doesn't exist. Well, another popular method is to use polar coordinates. B, using parametric functions. So, parametric functions. X equals to r cosine theta and y equals to r sine theta. Okay. So it means that wherever you see x, you write r cosine theta. Wherever you see y, you write r sine theta. So let's take a look at this. You have a limit of r squared cosine squared theta minus r squared sine squared theta divided by r squared cosine squared theta plus r squared sine squared theta, and r goes to 0. You're actually using a circle, its radius is shrinking because you have the origin, so the radius of your circle is shrinking. Let us simplify this. We get the limit of r squared cosine squared theta minus sine squared theta divided by r squared cosine squared theta plus sine squared theta. R goes to 0. We can cancel out r and r squared and r squared. On the denominator, you have 1, so the limit is equal to cosine squared theta minus sine squared theta. You have an expression depending on a new variable. So since our expression depends on theta, the limit does not exist. Why is that? It has contradiction with the uniqueness of the limit. I can select theta to be an angle, you can select theta to be a different angle, so we get different values for the limit of this function, and the limit doesn't exist. Let us go over another example. So A, y equals mx, y equals to mx squared, mx cubed, or any function passing through the origin. This is our second example. It says find the, check to see if the limit exists, xy divided by x squared plus y squared. Again, We can use any of these functions that help us to simplify this rational expression. So let us use y equals to mx. You might say, why we don't use x equals to my? That's fine. Why not? X equals to my. X equals to my squared. X equals to my cubed, and so on. As long as the function or the path passes through the origin you're fine. Okay, here you get the limit of x times mx. So wherever I see y, I replace that with mx divided by x squared plus parentheses mx squared. Let's see, after simplifying this expression, is this dependent on m or not? Note that I got rid of the variable y, so I'm just using a simple limit in x. I have the limit of mx squared divided by x squared plus m x squared, while x goes to 0. So we have the limit of mx squared divided by x squared 1 plus n squared, and x goes to 0. So let us cancel out x squared and x squared. As you can see, unfortunately, this limit simplified into m over 1 plus n squared. So since the limit depends on m, it does not exist. Okay, now let us use the second method to check to see if it matches the result that we actually have here. You have limit of r cosine theta times r sine theta divided by r squared cosine squared theta plus r squared sine squared theta, while r goes to 0. Your circle is shrinking because you're finding the limit toward the origin. That's why we send r to 0. This is equal to the limit of r times r, you get r squared cosine theta sine theta divided by, here I'm factoring out r squared, so what's left? Cosine squared plus sine squared, and r goes to 0. Now I can cancel out r squared, and this guy is just 1. So the limit depends on theta. This is equal to cosine theta times sine theta. So the limit depends on theta. So it contradicts uniqueness of limit, and limit does not exist. That's the reason. So on page 3, we have 2 checkpoints. Please take your time, think about these two, apply either of these methods. Page 3, checkpoint 1. It says check the limit of you have limit of the function x y squared. Now you have different powers, so try to figure out which function is more appropriate here, divided by x squared plus y to the fourth, while x and y goes to 0, 0, and checkpoint 2. Here you have this function. Show that the limit of the function x y squared divided by x squared plus y squared near the origin is 0. Okay, perfect. So let us start. For the first one, you might say, okay, I'm going to try to use, let us try to use y equals to mx. Okay, then I get a limit of x, mx squared, divided by x squared plus mx squared, and my x goes to 0. There you go. So here you end up with the limit of x, m squared, x squared divided by x squared plus m squared, x squared, while x goes to 0. So here you have the limit of m squared, x cubed divided by, here if you factor out x squared, you get 1 plus m squared, x goes to 0, so I can get rid of x squared, and I'm left with plus x squared times x here. Since x goes to 0, this is equal to 0. Or you might say, hey, I want to use, I'm sorry, I solved it differently. This is 4. Okay, let me just correct this one. I didn't see this down here. 4. M to the 4th, x to the 4th. So here you get the limit of m squared, x cubed, divided by, here you can factor out x squared, you get 1 plus m to the 4th, and x squared, while x goes to 0. Okay, perfect. So here you have, it's equal to m squared times x divided by 1 plus m to the 4th x squared, while x goes to 0. Okay, so your function has a function that actually has x in it. So you need to try to find the limit while x goes to 0 from right, while x goes to 0 from left, and check to see if those are equal to each other or not. Now, we need to take the limit while x goes to 0 from right, x goes to 0 from left, and check to see if the limit exists or is it equal to 0 or not. Again, that depends on different values of m as well. So it doesn't give us anything straightforward. Let us use a different function. Let us use x equals to m y squared. So if x is equal to m y squared, you get the limit of m y squared divided by m y squared to the second plus y to the fourth. And here your y goes to 0. Let us simplify this. You get m y to the fourth divided by y to the fourth, and inside parentheses, you get m squared plus 1. You can simplify this, you get y to the fourth, y to the fourth. So as you can see, the final answer, m divided by m squared plus 1, depends on m, so it doesn't exist. We can use y equals to square root of mx. So here you have the limit of x, mx. So since it has square root, and you raise it to 2, you get mx divided by x squared plus, here you get mx squared, x goes to 0. You get the same thing. So as you can see, you have different options, many options, which is equal to the limit of mx squared divided by, you can factor out x squared, 1 plus m squared. Now x goes to 0. So here note that my y approaches 0, now my x approaches 0. So if you take different functions, you get different variables. Here you can cancel out x squared and x squared, you get m over 1 plus m squared. Again, the same argument. Depends on m. So, limit does not exist. Let us check the graph of this function. So on the numerator, we have x, y squared, x, y squared, and on the denominator, we have x squared plus y to the fourth. Okay. Of course, the limit doesn't exist at 0. Yeah, you see, the function behaves crazy. Very well. So checkpoint 2. Let us find, check to see if the limit of this function exists, and if it exists, let's show that it is equal to 0. So I'm looking at the function itself. On the denominator, I see x squared plus y squared. So I quickly say, hey, let us use parametric functions. So there you go. For polar coordinates, in this case, you have x equals to r cosine theta, y is r sine theta. So in this case, you have limit of r cosine theta, r squared sine squared theta divided by r squared cosine squared theta plus r squared sine squared theta, while r goes to 0. So it is equal to the limit of r squared sine squared theta cosine theta divided by, if I factor out r squared, in the parentheses I have cosine squared plus sine squared. And r goes to 0. So if you cancel this out, this is 1. This is just a quantity, it's just a constant, depending on the values of theta, but r is here. Your r approaches 0, so the whole thing is equal to 0. Okay, I'm going to show you another method to show that the limit is equal to 0. If you remember squeeze theorem, sandwich theorem in Math 1A, you can actually apply that theorem here. Recall that. So, second method to solve checkpoint 2. squeeze theorem or sandwich theorem. This theorem says if you have three functions, f, g, and h. If you know the limit of g, if you know the limit of h, and they are equal to each other. So if limit of g is equal to the limit of h at a specified point, it is equal to, for example, a constant L, then squeeze theorem says that since the limit of these two functions are equal to each other, the limit of f, then the limit of f must be equals to L as well. Very well. So I'm erasing this part. Okay, let us start. This is the function that you have. I'm going to use some part of it and apply squeeze theorem. So consider y squared divided by x squared plus y squared. I didn't write x. I'm just forgetting about x and I'm using y squared divided by x squared plus y squared. I'm creating this function, function f, in the squeeze theorem. Okay, so note that for this fraction is always between 0 and 1. Y squared divided by x squared plus y squared is always between 0 and 1. Why is that? Your denominator is greater than the numerator. It's like if you want to imagine a number, it's going to be like 2/3. Or, I don't know, 1/4, a third. This is always between 0 and 1. The denominator is greater than the numerator. The denominator is greater than the numerator. Now what? Now I want to multiply all of these by absolute value of x. Multiply all by absolute value of x. Let's see. Absolute value of x times 0 is 0. Less than equals 0. Here I have absolute value of x times y squared divided by x squared plus y squared. You could say that, hey, why we are using absolute value? Let's just assume x is positive. You can say that as well. Less than equals to absolute value of x. I'm multiplying all sides by absolute value of x. So what do I have here? I have 0, which is my g. I have absolute value of x, which is my h. The limit of 0 is equal to the limit of absolute value of x, while x goes to 0. This is always 0. So, squeeze theorem says the middle function has always limit equal to 0. So, the limit of absolute value of x, y squared over x squared plus y squared, while x goes to 0, x and y, both of them are going to 0 and 0, is equal to